Hi, Cheyenne here. Today I'm going to talk about another problem in strength of materials, mainly about flexural capacity and bending shear force and bending moment diagrams. So let's see what this question asks us to do. So it says that symmetric cross-section shown below is made up of 6 timber pieces and is subjected to the loads as indicated on the left. So this is the load diagram that we have to deal with. Of course, based on this, we're going to find the reactions and then draw the shear force and bending moment diagrams, determine our highest moment, and then from that we're going to go to cross section, determine the moment of area, determine the moment of inertia, of course after finding a neutral axis, and then we will be able to basically use the flexural formula that we know to basically find the stresses, and then basically that's what the question is about. So you see, draw first the shear force and bending moment diagrams, of course a necessity in finding the flexural capacity, or basically the flexural stress on the beam, and then find the location of the neutral axis and evaluate the moment of inertia. Find the maximum stress at a layer located just below the circular hole. So this is very important, right? We're going to talk about it because we know the maximum stress occurs when, of course, at a point where the moment is maximum in the beam, but when you cut that section, the stress at this level is different from this level and different from the neutral axis and different from the bottom fiber, right? So all of these stress values are different. So we have to pay attention to the question. The question says just above the circular hole. So we're going to find that. And then it says determine the tension and compression forces and find the resisting moment based on the average stress value. So after, of course, we know how to use the flexural formula, we can find the stress at any point on the beam, at any layer on the cross section. So based on that, we can easily find the forces. Write the shear force and bending moment equation for portion CD based on the origin that's given, which we can do. Of course, we're going to cut it and take either the left side or the right side. We're going to do it both ways. And it is considering that the strain is given like this, determine the maximum load intensity that can be applied. So it says assuming that the strain value is given at this point, find the maximum W that can be applied. We're going to talk about that as well. And it says, let's say a hollow rectangular section made up of 4 150 millimeter times 450 millimeter is going to be used instead. So it means that instead of this section, we're going to use a section that is made up of 4 of these pieces. And we'll compare and see how this is different from the values that we get from this cross section, and we'll evaluate to see if this section is actually going to be safe. So let's start with our shear force and bending moment diagrams. The first step for finding shear force and bending moment diagrams is to find the reactions, right? Because for shear force diagrams, we need our reactions. So how can we find the reactions? So always, as we know from physics, the statics, we know that basically we have to draw the free body diagram of the beam, right? So we'll have a reaction at point B and reaction at point D, right? Of course, we're dealing with a pin and the roller. It doesn't matter where they are. In this case, we're basically neglecting axial load because there's no axial load that we can see. And of course, this structure is not determinate, or basically it is determinate, and we're not dealing with like a frame type of situation. So basically axial load here is neglected. Also that, of course, the stiffness throughout the beam is also the same. Now, of course, here we can find the moments by basically finding reactions based on taking the moment about any of these points, point B or point D. Why? Because if we take the moment about point B, basically this reaction force goes through this point. So what does it mean? It means that the moment that this force creates about this point is 0, right? The lever arm is 0. So what happens when we are writing the equilibrium equation for the moment? Then we are eliminating one of the unknowns. Why? Because we have 2 unknowns, right? So when we eliminate one of the unknowns, we end up with one of them. Basically, we end up with 1 unknown and 1 equation, and we can easily solve for the other one, right? So that's why we always, when we want to find the reactions, we take the moment about either this point or this one, or any of the reactions, right? Because we want to eliminate one of the unknowns, right? So first, in this case, we take the moment. Of course, we have to find the reactions. We take the moment about point B, right? And you can take it, of course, about point D as well. So what does it mean? Okay, we're taking the moment about point B. First of all, we have to consider that we have to just take it out of our imagination that there is any basically reaction, basically support here, right? There's no support. So this is just like a, let's say, a ruler, right? And you're just applying loads here, right? Applying loads. So about this point, right? This is, let's say, there's a, like your support, let's say your fingers for this ruler are here, and you're applying load with your other hand here, here. And that's how we're going to think about the sense of turning or direction for these moments, for positive convention. So in this case, of course, to say that we are taking the summation of the moments about point B to be equal to 0, we need a convention. We need to know which basically direction is positive, which sense is positive, and which sense is negative. So in this case, we are going to go with the counterclockwise as the positive sign convention. Okay. So here, let's start from the left. Okay, let's see what the deal is. So here, we start with a triangular load here, right? A triangular load. So here, we have to know what the moment of this is about point B. How can we know that? Well, first of all, this triangular load. We have to find the equivalent load. What is the equivalent load? We know it is basically always the equivalent load is the area under the distributed load, right? What is the area for this triangle? It is 10 times 6 divided by 2, or 30. Here it is 10 times 6 divided by 2. But where is it located? Because we don't know the lever arm, right? We know the force, right? Because we know what is moment. Moment is force times the lever arm. So the force is known, 30, right? 10 times 6 divided by 2. But what is the lever arm? The lever arm is, for a triangular load, is located a third from the edge. Okay? A third from the edge. So in this case, what would be the lever arm? So this is the load, right? So a third from the edge, what does it mean? It's 6 meters. What is a third of 6? It's 2 meters. So it means that from the edge to the centroid, it's 2 meters. So it means that what is the lever arm? 6 minus 2, or 4. So this is the lever arm we're looking for. So basically this was the force, and this is the lever arm. So that's why we say the magnitude of the force multiplied by 4, which is basically the lever arm. Is it positive or negative? Well, this is the point, right? And we're applying load in this direction. So obviously it's going to turn the ruler in this direction, right? Turn the beam basically, right? Turn it in this direction or counterclockwise. What was our positive convention? It is counterclockwise positive, so positive. Now let's move to uniformly distributed load, right? Here we have 5 kilonewton per meter over 10 meters of length. So what is the moment that this creates? So we have 5 times 10, magnitude of the force, which is going to be in the middle, right? And also don't confuse it with this 30 kilonewton load, right? So this is a separate concentrated force. So basically it has nothing to do with the force, the magnitude of this distributed load. 5 times 10, 50. So 50 in the middle. And what is the lever arm? 5, right? It's half of the distance. So it's going to be 5 times 10, the magnitude of the load, times the lever arm. What is the lever arm? 5. What we have here. It's negative or positive, of course, it's turning. We are talking about this point. Turning it in this direction, right? So it's going to be clockwise or negative. Why? Because our positive convention was counterclockwise. Here, now let's talk about the 30 kilonewton force. Again, this 30 kilonewton force multiplied by 5, right? Because it's midpoint, right? C is midpoint. So times 5, it's going to be our moment. Again, 30 times 5. But is it negative or positive? Again, it's going to be negative because it is clockwise in this direction. Now let's talk about dy. So for dy, we can say that, okay, it's dy multiplied by 10, right? About point B again. Remember, we're all taking all the moments about point B. dy multiplied by 10, right? But is it positive or negative? It's going to be, the turning is in this direction, right? This direction. So what is going to be? Counterclockwise or positive. Now let's talk about the moment. So this is a concentrated moment, remember, right? So this is not a load. So we can't say 50 times 11, right? So this is a concentrated moment, so we just have to take it into account. In what direction is it? Is it clockwise, counterclockwise? It is clockwise. Clockwise is negative. There you go. And then we have this 20 kilonewton load. So 20 multiplied by 3 plus 1 plus 10, which is 14, right? So 20 multiplied by 14, but is it negative or positive? It's turning it in this direction. What is this? It is clockwise, so it's negative. There you go. So the summation of all of these moments is going to be 0. So if that's the case, we can easily solve for dy, right? And dy is 61 kilonewton. So a very important point here is that if you get your dy as negative, what does it mean? it means that the direction that you assumed for dy reaction was not upward, right? It is downward, right? It was basically the opposite of the assumption that you made. Same for by, for example, for by, let's say you find negative 52, right? Then it means that by was basically going down. But remember, we have to be consistent, right? So what I would always do to just basically avoid confusion is just, if you get this as negative 61 kilonewton, right? You can just, in the bottom, just draw this again, right? Draw only this one again, downward. And just indicate this is the correct, basically, dimension, or basically correct direction, right? And that way you can continue your calculations, let's say for the summation of the forces in the vertical direction, based on that, so that you don't have to worry about putting it in negative way, positive way. You can just go with your positive convention without worrying to basically say, okay, did I get negative here? So for dy, in the future calculation, should I put negative? So to avoid that confusion, just change it instantly. So when you see this, change it instantly in the bottom. But let this be here for, your calculation, because, when you come back to this calculation, you might say, okay, why did I do that, right? So just change the calculation constantly, like instantly, and change the direction instantly after that, and then everything will be fine. So now we just have to go with the summation of the forces in the vertical y direction, right? Like this, right? And of course, again here, I go with the positive convention of upward means positive, right? So in that case, I'll again start from the left. I have 10 times 6 divided by 2. That's my magnitude of the force, right? It's negative because it's going down, right? 10 times 6 divided by 2, or negative 30. So negative 30, and then compare here, now by. Do I know by? No, so but it's plus by, there you go. And then I have 5 times 10 going down, so negative 50 going down, there you go. Negative 30, and then positive dy, right? Positive dy. So here my dy is 61 kilonewton. So again, going back to the previous point, if you found d1, let's say negative 61 kilonewton, it only means that you can draw this again like this, right? So remember that in the previous step, we draw it like this now, right? After this step, if this is negative, we draw it like this. Now when you're doing your sigma fy calculation, you go with this one, right? So you say minus 61 kilonewton based on this, okay? So that just makes it easier. But now we're not dealing with a negative case here, so we'll just go with our calculation, plus 61 kilonewton, there you go, and minus 20. Another important point, this is a moment, right? This is not a force. So that's why we do not take it into account in our vertical force calculations, right? So again, based on this, we can get our by value, which is 69 kilonewton. Now, basically, we have both of our reactions. We have by and we have dy, okay? Basically, now we are prepared to draw our shear force and bending moment diagrams. So this is the reaction we found for by, and this is for dy. So let's start with our shear force diagram. Basically, what shear force diagrams represent is the vertical forces that apply on the beam, right? So the basically forces that are vertical to the beam are represented in the shear force diagram, right? So only the loads, right? So it's just one step ahead. So we're dealing with the vertical force that exists at any point in the beam, right? It's like, of course, you have probably studied about sectioning before. So when we cut a section, that's exactly the value, right? When we cut a section, what do we deal with? We deal with a normal force, right? Axial force. We deal with a shear force, and we deal with a moment. So you see, like that shear force is basically this. And the only thing we're doing is just drawing a diagram for it, right? But what we're going to do is just avoid, just using section, right? Because if you have to section, you have to section whenever like the load changes. So you have to section once here, you have to section here, you have to section here, you have to section here, and you have to section here, right? But do you want to do that? We have to section it. So probably for shear, we don't have to divide this into two parts. But do we want to like basically section 1, 2, 3, 4 times at least? That'll take a lot of time. So let's just look at basically the best way to do it is just look at our load diagram, and based on that, draw our shear force diagram. So at first, let's start with like the points, right? Always we have to pay attention to the critical points that we see. or the points that we see in the beam, basically A, B, C, D, E, and F, right? Probably for the shear force diagram, E will not be that important, but we'll see. So here, we start with point A. Is there any shear for point A? There's no shear. Why? First of all, what is the meaning of shear? Shear force is created based on the two surfaces that are in contact. At point A, how many surfaces do we have? It's the edge of the beam, right? We only have one surface. So basically shear force is not really defined there, right? So shear is 0 basically, right? Because there are no two surfaces. So here we start with 0, right? Always, just you can, have this in your mind as a tip that at any point when you start from the left or right or however you draw your shear force diagrams, your shear at the start will always be 0 unless there is a reaction. So let's say this By here was here. Then you would go up, let's say by 69 kilonewton here at the start. If your By was here, we had a reaction, right? But if there's nothing, you start with 0 for your shear force diagram. Easy as that. So we start with 0. And then we don't have any points here. So point B, we have to know what the shear is just to the left of support B at this point, right? How do we know that? We can look at our diagram and say, okay, what is the change in load? At point A, the shear is 0, right? But what is the change in load from A to B, right? Basically, we can remember this, that the area under the loading diagram represents the change in shear. So here, what is the area here? What is the total change in load from A to B? It is 10 times 6 divided by 2, right? This is the total magnitude of this triangular load. So 10 times 6 divided by 2, or 30. We are going down 30 from A to B. So at A we had 0. At B we will have negative 30. Okay, like this. But, so there are, of course, we know that, okay, this point is 0. This point is negative 30. Okay, now we know that. And of course, this point is just to the left of B. Just to the left of B. But how do we know this is a parabola or a third degree, fourth degree? How do we know? Again, we just have to look at our load diagram. So again, let's review. When you have a triangular load like this, you see it's a line. It's a first degree curve or a line. Your shear diagram will be basically kind of upgraded to a second degree curve or a parabola. Your moment diagram will be a third degree, right, from A to B. See? So here you have a line, you have a triangular distribution, a first degree curve. Here you will have a second degree curve, here you will have a third degree curve. For example, for a uniformly distributed load, you see this is a constant line. This is a 0 degree curve, right? Constant line. So a 0 degree curve will be upgraded to a first degree curve or a line, right? So we will have a linear trend here. And for the moment, we'll have a second degree curve or a parabola, right? For the whole, basically from B to D. And then here we have nothing, right? So we have no load. Load does not exist in terms of distribution, right? In terms of the distributed load, right? So when distributed load does not exist here, it means that for the shear force diagram, you're going to deal with a 0 degree curve, right? Or a constant line. And for the moment diagram, again, updated. A first degree curve, right? For a moment will be a line, right? Simple as that. So if you remember these, that will be enough for our basically drawing our shear force and bending moment diagrams. But of course, the idea behind this is just integration, right? Because it has to do with sectioning, and of course you can find the proof. It's basically one of the basics of drawing a shear force and bending moment diagram. Of course, in some cases you might even have this as a parabola, right? And probably in your book, you can find examples representing a parabola, and the equation is even given, right? So the only thing, again, we have to do is just integrate this one, right? Integrate, for example, if this, let's say, equation is given, you just integrate that one, and basically draw this one, integrate this one, draw that one. Easy. It's basically, that's the concept behind it. But for our purpose, the ones I mentioned are going to be enough. So here we are here again now. Now, for the 6 meters, we know that it's 0 to negative 30, right? And we know it's a parabola. It's a second degree curve. But for a parabola, we can go like this, and we can go like that, right? We have two options. How do I know which one, how I should go? What is my way of knowing? We can know it basically by considering that the intensity in the loading diagram, represents the slope in the shear diagram. So you see, so this 10 kilonewton meter that you see here, 10 kilonewton per meter, intensity, which means basically that your shear is, that the slope in your shear diagram is 10. So this slope is 10. And of course, as you see, the intensity is getting smaller. What does it mean? It means that the slope you have here is going to get flatter. Of course, I'm not going to mention negative or positive slopes, just to avoid confusion. Obviously, this is a negative. This is the force is going down, right? So this is a negative slope here. But yeah, so we're only going to consider intensities and the magnitudes. So you see, it is intense here, and then the intensity goes down, which means that you will have a large slope here, and then after this, you're going to deal with a flatter slope. Okay, and at the end, at point B, what is the slope? Just to the left, it's 0, right? So here, in the loading diagram, your intensity is 0, which means that the slope is for the shear diagram is 0, right? Simple as that. So that's how we draw our shear force diagram from point A to B. Now let's move forward. At point B, what happens? We have a reaction. 69 kilonewton going up. So simply, the change in load, what is it? It's positive 69. So negative 30 plus 69. There you go. Then we have a distributed load. But the distributed load, of course, goes from B to D. But we'll evaluate first from B to C. Why? Because we have another load in the middle. We have to take that into account as well. So we'll say, okay, positive 39. We have it at point B. It goes that, what is the change in load from B to C? It's 5 times 5, right? So this from B to C, we have 5 meters, and the intensity is 5. So 5 times 5 is the magnitude of the load, or the total change in load. And of course, it's going down. So it's negative 5 times 5, or negative 25. So positive 39 minus 25, we're going to end up as positive 14. And then you have a 30 kilonewton load going down. So positive 14 minus 30 is going to be negative 16. And then again, we're going to go down another 25, right? It's 5 times 5. Negative 16 minus 25, it's going to be negative 41. Now we are at point D. At point D, again, we have another reaction. It's going up. So negative 41 plus 61, it will be positive 20. And then from D to F, there's no load, right? There's no vertical shear force. Again, this 50 kilonewton meter is a moment, right? We're not dealing with moments here. We're dealing with shear forces. We're dealing with basically magnitudes of loads here. Loads like this, vertical loads. So here from D to F, again, is there any load? No. So it will just remain 20, right? It will be constant, 20. And finally, we have a 20 kilonewton load going downward. So we'll go 20 downward and we get to 0. And that is great because we know that our structure is in equilibrium. So obviously our shear force diagram should end with 0, right? At the start, at the end, it will end with 0, right? We know that. Otherwise, our shear force diagram is not correct. And of course, remember, unless, for example, when you start from the left side, don't confuse it with the reaction, right? Even with the reaction, let's say we had a reaction here. Let's say positive against 69, right here. We had a reaction. You would, again, start with 0 and go up 69, right? So again, you're starting with 0 and you're going to again here end with 0. Okay, and that's how you know your shear force diagram is probably 99% correct. So that's how we draw our shear force diagram. Okay, now we are prepared to draw the moment diagram. So we draw the moment diagram based on the shear force diagram. So it's the moment diagram. Of course, the units are kilonewton meters. And let's start. So the same concept that applied from the load diagram to the shear force diagram will apply from the shear force diagram to the moment diagram, right? Meaning that, again, you still remember for the load diagram, the area under the load diagram represented the change in shear. In other words, the change in the total magnitude of change in load is basically the change in shear here, right? Here again, the same concept applies from shear to moment. The area under the shear diagram represents the change in moment. Okay? But you might think, okay, wait a minute, we're dealing with a parabola here. What is the area of a parabola? There are tables for that. Of course, you can use those tables to find the area of this parabola. Pretty easy. But let's say we don't have that luxury, right? We don't have access to that table. Okay? How can we know the moment at just to the left of point B, right? Because as we know, again, these are the critical points at point A, B, C, D, E, F. These are the points that we are concerned about mainly. Just to the left of B, we want to find the moment, right? Because we want to draw our moment diagram. What we do is basically just a fast section cut, right? Just in our minds. We're not going to draw everything, right? We can just do it in our mind. How? Let's say we cut a section here. Of course, we will have a shear going down. We have a moment in the basically this direction, which is counterclockwise, basically in the direction of compression at the top. What is that moment, right? Of course, that is a conventional moment, right? In that case, the moment will be negative, which is exactly the case here. We're going to deal with a negative moment. We're going to talk about it, so I don't want to confuse you with all those conventions. But we have a moment here, right? That's the final idea. What is that moment? Well, you say, okay, we have a shear here, and we have a moment. What I'm going to do, I'm just going to take the moment. So let's say we cut the section here, and we took this out. And we have shear and moment. You take the moment about just to the left of B, just to about where you cut. And I will emphasize this point again and again. Always when you're cutting a section, take the moment about where you cut. That is going to help us immensely, right? In calculation, in avoiding extra calculation. And in this case, think about it. Here we have a shear force and moment. And we are only concerned with moment here, right? We want to find moment here for the moment diagram. And although like we have access to shear here, right? But let's say in most cases, we don't need the shear. So in this case, let's say I don't want to deal with the value of shear. I don't want to find it. That's extra work. So what I do is just take the moment about this point where the moment effect of the shear is going to be 0. In other words, the lever arm for the shear force is going to be 0 about this point, right? Because it's going through that point. Of course, you will understand this point better when we are dealing with a section cut in, I think, question 5 or 6. So in this case, we just take the moment about again. What we did only, the only thing we did, just cut the section, take the moment about like where you cut, okay? And based on that, what is the moment that you're going to find? It's going to be 10 times 6 times 4, right? 10 times 6 times 4, 10 times 6, but see, sorry, 10 times 6 divided by 2, which is the magnitude of the force, multiplied by 4, which is going to be 30 times 4 or negative 120, right? Simple as that. How did we know it is negative? Well, look at our shear diagram. What is the change in shear? Basically, what is the area under the shear diagram? It's negative. So we know it's going to be, the moment is going to start from 0 to negative 120. Before I forget, again, why did we start our moment from 0? Because there's no, moment, the concentrated moment for this, right? Basically, you start your moment diagram with 0 when you have no fixed support and no concentrated moments. Okay? So when you have no concentrated moments and no fixed supports, you start with your moment diagram with 0. If you do, we're going to deal with it at point E, right? So what did we do? So from 0, and it's negative 120, right? So we know these 2 points, 0, negative 120. How did we draw this? So again, remember, second degree curve, the moment is going to be a third degree curve, right? And we want to go from 0 to negative 120, right? How do we go? Do we go like this? And do we go like this? And someone might think, okay, why is it not going like that? Or why is it not going like this or whatever? Well, the reason is pretty clear. So if we go like this, what happens? It means that basically our moment will be going up in some case. So if let's say this is the case, is our moment going up? No, because our shear, you see like the area under the shear diagram, it's all negative. It means that it's just start from zero. Our moment start from zero and then just goes down. Right? It's all negative. So it means that your moment diagram from A to B is all under this, this negative, all negative. So it will either go like this or go like that. Now, how do we know which one that is? Again, remember the point that we mentioned about shear. How did we know this? Well, we said the slope for the shear diagram is the intensity of the load diagram. Same concept applies from moment to shear. The slope for the moment diagram is the shear value here. So here, what is your shear value here? 0. What does it mean? It means that the slope is 0. Here. See? So we start with 0 slope. Then here, as you see, the value of shear increases, right? In terms of magnitude. It means basically that your slope is getting steeper. So you start with a flat slope, and then your slope increases, and here you have the largest slope because you have large shear value. Now we're done with this, right? So that's why we draw it like this and not like that, right? Because if you draw it like this, what happens? It means that first of all, your slope in the beginning is not 0, right? And your slope must be 0. And at the end, your slope is kind of like flatter, but that is not the case, right? So the whole idea is that the value of shear represents the slope of your moment diagram. That's all. So now we're done with part AB. Let's move forward. So now let's look at our shear diagram here. From this point to this point, what is the area here? We have to calculate. So again, the area under the shear diagram is the change in moment. So from 14 plus 39, which is like 53, multiplied by 5 divided by 2. Just the area of this trapezoid, right? The smaller base plus the larger base, multiplied by the height divided by 2. Right? That's the area of this trapezoid. That will be the change in moment from B to C. So we'll add that value to negative 120, right? So basically that value was positive 132.5. So negative 120 plus 132.5 is going to be positive 12.5. Now, of course, by the way, how do we know that the change is positive or negative? Is obvious, right? So the area under the shear diagram is positive, right? Positive. And that's why we say negative 120 plus 132.5 gives us this value. And again, let's look at why we draw it like this, why we didn't draw it like that. Let's look at the intensity. The intensity in the beginning of the shear diagram here at point B is 39, large, and then the intensity is getting smaller. It means that the intensity, the slope that we have, is steep, and then it becomes flatter. Again, see what we did. This slope is steep, and then it gets flatter. Easy as that. But remember, it's not 0, right? So you shouldn't draw a 0 slope here. It's not flat like this, completely flat. So it has there's some slope. The slope here is 14, right? So we only represent basically the larger slope, smaller slope, right? At point C, again, let's go to our diagram. We have this. So we say again 16 plus 41 times 5 divided by 2. And we see minus that, right? So we say 12.5 minus the area under this. So we go like this. So we're going to end up with negative 130. But let's take a look at this. So first of all, as you see, the intensity here is small, right? And then the intensity gets up. Of course, and again, when I'm talking about the shear value, I'm talking about the magnitude, right? The magnitude here is small, magnitude is here large. So here we have a flatter slope. Here we have a steeper slope. So start again with a flat slope and go steep, right? Flat slope. So whatever, we know what flat means, right? So these are flat and this is like steeper, right? Flat and steep. But here someone might ask again, like, why is it not like this? Well, if we draw it like that, it means that here we start with a large slope and then go flat. But that is not the case here. We start, the intensity here is small and the intensity here is large, 41, right? So we start with the flat and end with the steep. And of course, remember again, about all of this again, I'm repeating this again and again because it's very important. This was second degree, here we have third degree. This one we have first degree, second degree, first degree, second degree. This is a constant line, right? Constant line, which means it's a 0 degree curve. Here we're going to end up with a first degree curve or a line. So from D to F, you're going to have a linear trend. So at point D after point D, we have this shear diagram here, right? So someone might do, okay, 20 times 4, 80, so positive 80, so negative 130, positive 80. Oh, wait a minute. We did not end up with 0. So what is the problem? There it is. At point E, we have a 50 kN/meter moment. We have to take that into account now, right? Because we are drawing the moment diagram. How do we take that into account? First, these are separate parts for the moment, right? For the moment diagram. So we evaluate first from D to E. So let's go to our shear diagram. D to E, right? So here from D to E, here is 1 meters, and this is 20. So 20 times 1 is the area under the shear diagram. So the change in moment is 20 times 1, right? So see negative 130 plus 20. That's going to be negative 110. So your moment at this point is negative 110. But then you have a concentrated moment here. A point that you should remember here to draw your moment diagram. Clockwise concentrated moment means a jump or going up in your moment diagram. A counterclockwise concentrated moment means a drop going down in your moment diagram, right? So here we have a clockwise, meaning that negative 110 plus 50. So we'll go up by 50. And we'll end up with negative 60. Okay? And after this, again, we just continue with our shear diagram here, right? So we have 3 times 20. So negative 60 plus 60, we're going to end up with 0. Perfect, right? Because that's what we wanted, right? We want to end up with 0 on the left and 0 on the right. Now let's say again, at the right you have a fixed support. At the right you have a concentrated moment. Again, at the end, let's say we end up with like negative 20, and of course at the end we will have a clockwise moment, right? At the end again, my point is just we end up with 0, right? That's how you check. So meaning that at the end your line goes to 0. Doesn't matter if it's vertical, if it's like horizontal, if it's linear, parabolic, doesn't matter. It just gets to 0. It starts with 0 and gets to 0, right? And again, another point, if like we had a fixed support here, if you had a constant moment here, at first you might have a jump or you might have a drop. Again, you start with 0. You go from 0 to, let's say, 30, 60, 70, whatever your concentrated moment was. Or you drop, let's say, from 0 to negative 30, negative 40. But again, you see, like you start with 0. And that's the whole concept for equilibrium. You start with 0, you end with 0. Okay? And that's it for our moment diagram, right? Again, for the last part, this is a constant, this is linear, right? So remember that concept about upgrading the degree of the curve, okay? Now that we have our shear force and bending moment diagrams, we're basically prepared to evaluate the flexural formula and see what the stresses are all over the beam and at each layer. But before that, let's say in your shear force diagram, you're dealing with a concept like this, right? So this has nothing to do with the question that we're doing, right? So this is not a replica of our question. It's just a random question. Let's say at one point of drawing your shear force diagram, you end up with something like this, right? So you draw this, 30, and you go down by 7 times 10, negative 70, 30 minus 70, you end up with negative 40. To draw your moment diagram, you have to know the area of this, right? And the area of this. But how do you know the area when you don't know x? So it means that when you have a situation like this, you have to find this distance and this distance, right? In order to draw the moment diagram. But how can we do that? The basic idea is basically the similarity of triangles, right? So here you can see that this triangle, right? The simple idea is that this triangle is similar to this triangle, which is true. This triangle and this triangle are similar. But the problem is here, if this is x, right? What is this? This is 10 minus x, right? So from here to here is 10 minus x. So, and when you write an equation for the similarity of triangles, you have to, multiply the sides and then just solve an equation. And, it's going to take some time. But in order to avoid that, what can we do? What I would like to do is just say, you know what, I'm going to take the similarity of this triangle and the large triangle that I have here, right? The imaginary. So if you have like some dashed lines here, let's say, this triangle. Okay. So the similarity of this triangle and this triangle. How does that work? Well, okay, for this triangle, again, I will say x divided by 30. X divided by 30 is equal to this distance, which is 10, divided by the whole distance from here to here. What is the whole distance? It's negative 40 minus 30, right? Or 70, basically. Again, like here, we're not dealing with magnitude. We are only dealing with magnitude, so don't worry about the sign. What does it mean? So what I mean here is x divided by shear on the left, we can remember it like this, is equal to total distance divided by total change in shear. So in this case, x divided by 30 is equal to 10 divided by 70. Simple enough. X over 30 is equal to 10 over 70. And how do we get 70? Of course, 30 minus negative 40. It's just the whole difference between this one and this one, right? The difference. And that's it. And this is a more efficient way of doing this, in comparison to, of course, saying that this is x, this is 10 minus x, blah, blah, blah. Okay? So in this way, you can find this one, and based on that, draw your moment diagram. If you see basically a situation like this, which probably you'll see. So that's why I mentioned this. So this is very important. Of course, it's much better to do this like when you draw your shear diagram and you finish your shear diagram, just, instantly go to this one, and that's it. We're done with our reactions, shear force, and bending moment diagrams. Okay, and remember what the equation is for the flexural formula, right? So it's my over I. So now for m, which is moment, we have m. What is y and what is I, the moment of inertia? We don't know those, right? So y has a component of neutral axis in it. I also includes some components of neutral axis, and of course the capacity of the member to resist flexural deformation, which again has to do with the moment of inertia, second moment of area of this cross section. How can we do it? The first thing we have to do is find the neutral axis of this section, right? Of course, if the section is symmetric, about like this, about the horizontal axis that we have here, about the main global axis, or the major axis that it has, or about the axis that we're evaluating our section about, then in this case, let's say, for example, you have a rectangular section, then naturally the axis of symmetry is in the middle, right? That's your neutral axis. But in this situation, we don't know where the neutral axis is. It can be here, here, yeah, here it is, right? So we don't know where it is, right? It's just an arbitrary point. First thing we have to do is define a datum line, define a reference line. And usually the best thing is to either choose a top fiber, or choose the bottom fiber as your reference lines. Meaning that when we are trying to calculate our y bar, right? Y bar, and we know what y bar is, right? Y bar is sigma a y tilde divided by sigma a. That will be the position of neutral axis with respect to our reference line. So I chose my reference line to be the bottom fiber, right? Easy as that. You can choose a top fiber, doesn't matter. And with reference to this, I'm going to find my y bar. So let's define these. What is A? A is the area of each section, right? And when I say each section, we'll see like we're going to divide each section, divide this whole cross section to different sections so that it makes it easier for us. Then we have y tilde. Y tilde is the centroid of each single section. Let's say this is a section, like a single section. It is the distance from the bottom line to the centroid of this section. Simple as that. Okay, distance from the dotted line to the centroid of the section. For example, for this section, the centroid is here, so we are interested in this distance. Okay, simple as that. And a y tilde is basically just a multiplication, a times y tilde. So the first thing is to divide our section to different parts to make it easier for ourselves. We'll do it two ways, right? So this is the first way. We say, okay, that's number 1, number 2 for these these rectangles, number 4 and 5 for these small pieces, and number 6 for this one. and number 7 for this whole, right? This is a whole. We're going to subtract this one, okay? So let's start with our part 1, right? So basically what we're doing is calculating the contribution of each of these to the moment of area of the cross section. Again, don't confuse moment of area with moment of inertia. Moment of inertia is the second moment of area, right? Because you have a squared component in the moment of inertia definition, which of course you can find in your. I'm not going to go into theory. This is, strictly just problem solving. So here we have. Let's start with the first piece. For the first piece, what is the area? 300 multiplied by 100. 300 multiplied by 100. So we'll put 300 times 100 here. What is y tilde? Again, what is y tilde? It's the distance from the datum line, the reference line, to the centroid of that cross section. So from here to here. What is the centroid? It is 50, right? 100 divided by 2. So we'll just put 50. And then multiply this by that, a y tilde. Of course, it helps, of course, to use an Excel table or whatever you use to just make the calculation easier. Then for section 2, what is the area? The area is 400, right? From here to here, it's 100 plus 300 multiplied by 100 here. This is 100. Why? Because this is 300, and if this is 100, this is going to be 100, this is going to be 100. Okay? So here, that is 100. So it's going to be basically 100 times 400 for area. For y tilde, it will be the centroid here. So what is that distance? It's going to be 100 plus 400 divided by 2, right? So the centroid of this section 2 is here. So it will be 100 plus 400 divided by 2, right? 100 plus 200. Section 3, the same thing. Section 4, again, the similar ideas. It is 100 times 100 for your area. For y tilde, it's here. So what is it going to be? It's going to be 100 plus 300 plus 50, right? Simple as that. Section 5, same thing. Section 6 is going to be like this rectangle, right? And the area for this rectangle is 200 multiplied by 500. 200 times 500. Okay. And y tilde is 100. See, 100 plus 300 plus 100 plus 100, right? Because it's half of this. Simple as that. And at the end, we are dealing with the circle. Of course, the centroid of the circle is the same as the centroid of the rectangle, so the same idea. So these two values are the same. But the area is, what is the area of what's the area of a circle? It's going to be pi times diameter squared over 4, or pi times radius squared, right? Same thing. But the difference is, of course, here diameter is given, so we'll just put that there. But we just here put negative. Why? Because it's a whole, right? We're not adding it, right? It's not an extra circle, right? It's just a whole, so we're going to subtract this. So that's why it's negative. So we calculate all of this. We sum this column, we sum this column, right? And then we divide this by this, right? So we're going to end up with this value. Okay, simple as that. Of course, remember, we used all millimeters in our calculations, right? So we are going to end up with millimeters as well. This is millimeter squared. This is millimeter cubed, and this is millimeter squared. Millimeter cubed over millimeter squared is going to be millimeters. Simple as that. But some people might say, okay, you know what? This is not the most efficient way of finding a neutral axis for this section. Someone might say, actually, I'm going to use 5 parts rather than 7 parts. How? Well, some might say, you know what? I'm going to say that this whole rectangle here is one section from here to here. And then what I'm going to do is just subtract this section, subtract this section, subtract this section, and subtract this section. That way my calculation is going to be easier. And this is a smarter way to do it, for sure, right? So let's do it. So for section 1, the whole section, what is it? The area is 500 multiplied by this, which is 100 plus 300 plus 100 plus 200 is going to be 700, right? So 500 times 700 is the area, okay? So of course, this is the sections that we said, right? Section 1, section 2, section 3, section 4, and section 5, right? So remember again, section 1 is the whole rectangle, and section 2, 3, 4, and 5, we are subtracting. So here, if we start with section 1, we said 500 times 700, your y tilde is 350, right? Why is it 350? Well, it's just the centroid of this whole big rectangle, right? So 700 divided by 2, basically. 700 is this one, divided by 2. And then for section 2, again, you see like the same ideas. So I'm not going to go over it that much. So again, for section 2, again, this is your area. So 100 times 400, right? For area, for y tilde, you have this, the centroid of this, right? Which is going to be 100 plus 200 divided by 2, right? 200 divided by 2. Actually, 400 divided by 2. So 100 plus 400 divided by 2. And that's how we end up with that. Section 3, 4, very similar ideas. And section 5 is the circle, the area again. It's the same, we know it. And y tilde is just going to be the same as we had it before. And again, you sum up this column, sum up this column. The answer will be the same, of course. You know, it doesn't matter how you go about doing the question. It's just a matter of being consistent and knowing how to segment your sections, you know, in the correct manner, right? That's all, right? Of course, you know, both the methods, you know, are correct. The second method might be a little bit easier because it takes less time, but again, it doesn't make much difference. So now we know the location of the neutral axis. What is the location of the neutral axis? This is y bar that we found. It is 47.2 from the datum line. So this is the position of the neutral axis. Okay, simple as that. Now that we know that, we are prepared to calculate the moment of inertia of this cross section. How can we do that? Well, moment of inertia is the contribution of moment of inertia from all these different pieces. So what I assume, of course, you know, you can use like the 5 pieces as well, remember? So we had 7 pieces at first and then 5 pieces, right? So you can use either of them. I try to, you know, be like more, because it's easier just to consider different segments rather than, you know, like subtracting it for some people. But again, it doesn't make any difference. So you can go 1, 2, 3, 4, 5, 6, 7, as we did before, or again, like do like the whole section as 1, and then do 2, 3, 4, 5 for subtraction, right? Same thing. So you can go with that one too. But in this case, I went with the first method that we chose. So here it is. So these were the sections that we had, right? So the moment of inertia of the whole cross section is the contribution of the moment of inertia of each single piece, right? So here, the moment of inertia contribution of I1, I2, I3, I4, I5, I6 minus I7, right? This is very important because this is a whole. This is a circular whole, right? So we're going to subtract the contribution of this one, right? So all of these are added because these are actual pieces. I7 is a whole, so we subtract it. Easy as that. But what is this I1, I2, I3, I4, I5? We'll have to calculate those. What is I1? Well, what is the moment of inertia of a rectangle? So this is, we want to calculate the moment of inertia of this rectangle. It's base multiplied by height to the power of 3, right? Base times height to the power of 3 divided by 12. Easy as that. Here it is. 300 times 100 to the power of 3 divided by 12. But what this is the moment of inertia of this cross, this basically piece, about its own local axis. But we're not trying to find that. We're trying to find the moment of inertia of this section about the global neutral axis, right? Or the global centroidal axis of this whole cross section. How can we do that? How can we convert that? Well, in your theories, you have studied the parallel axis theorem. Parallel axis theorem, basically what it does is just convert this, the effect of the local effect of this moment of inertia and bring it to the centroid, or basically find the moment of inertia contribution of the section with respect to the global centroidal axis that we want to find our moment of inertia about. And what is the formula? It's just, you know, you have to add area multiplied distance squared, right? So parallel axis theorem says local contribution plus the parallel axis theorem contribution, extra contribution, which is the area multiplied d squared. Okay, so area is 300 times 100, right? We know this 300 times 100. And by the way, if you construct the table in the previous pages, you remember this one? If you construct this one, you don't even have to like calculate areas and other ones again, right? So you can just use it 300 times 100 by default. We don't have to look at our shape again. Multiplied by d squared. What is this d squared? d is the distance from the local centroidal axis to the global centroidal axis. Okay, so from here to here. And someone might think, oh my god, this is really complicated. From this shape, I have to again like see what is this from here to here. Again, I have to look at my numbers. But the answer is actually that is not what you have to go through. Let's not make it that complicated. Do you remember the table that we created here? And if you construct that table, that's it, right? You can just see what is d. D is going to be y bar minus y tilde for each part. Y bar minus y tilde. Simple as that. So y bar is constant for all, y bar is found, right, for 7.2. It's going to be constant. Y tilde is the one that's different, right? For each section, y tilde is found and it's different, right? See? And that's all we have to deal with. There you go. That's I1. I2 is going to be, again, pretty simple. 100 times 400 to the power of 3 divided by 12 plus area, again, we have area here, times d squared. What is d? We said y bar minus y tilde is squared. Y bar, we know it. Y tilde, there you go. Again, y bar minus y tilde squared. Y bar minus y tilde squared. Y bar minus y tilde, like you see, squared. Y bar minus y tilde squared, right? Again, squared is of course outside. And I7 again, y bar minus y tilde squared, right? Easy as that. So based on that, simply we can find our d squared, right? Simple as that, an area. But we don't have to look at our shape anymore. So these we know, right? These are just basic, simple rectangle. So for example, for I5, I'll do it. For example, I5, it's 100 times 100 to the power of 3 divided by 12. Simple as that. These are simple. But for I7, what is the moment of inertia of a circle? It is pi r to the power of 4, pi times radius to the power of 4 divided by 4. Or pi times diameter to the power of 4 over 64. You can use either. So I chose the radius one here. Pi times radius to the power of 4 over 4 plus the area multiplied by d squared, which we talked about. Now you add all of these together, I1 plus I2, I3, I4, I5, I6, minus I7, as we defined here, and you get your final moment of inertia, total moment of inertia of the cross-section. And this is what we want. Okay, simple as that. So here we have the moment of inertia.